Hello, welcome to this video. Let's continue to discuss some results on continuous topological spaces or discontinuous topological spaces. The theorem states that theorem 5.9 contains two statements. M states that X is disconnected, and the statement N says that X has a proper subset A which is both open and closed. How to prove this? For that we suppose that M is true, and then if M is true, then X is disconnected. Then X has a disconnection. X is equal to A union B, where A and B are open sets and A is non-empty, B is non-empty, A intersection B is empty. Now A and B are proper subsets of X. Then we have we have already shown that both A and B are both open and closed. See, A and B are proper subsets and they are both open and closed. By choosing one of these proper subset A, we get the property that A is a proper subset and A is both open and closed. Hence we get the statement N as a true statement. Conversely, suppose that N is true, then see, X has a proper subset A which is both open and closed, and we now we can take B equal to X minus A, since A is open and B is closed, since A is closed and B is open. Now B is also open, and thus B is also both open and closed, and A is non-empty, so B is also non-empty, and X can be written as the union of A and B, and A intersection B is empty, therefore X is disconnected. Thus we get that the statement M is true. Consider next this the theorem 5.10. Here we have the statements M and N. We want to establish the equivalence of the statement M is equal. M if and only if N. M states that X is disconnected, and N states that N states that X has a proper subset A such that closure of A intersection closure of X minus A equal to the empty set. Closure intersection closure of X minus A is empty set. So if M is true, then X has the disconnection using the open sets A and B, and we know that then A intersection, a part of that condition, part of the we know that one of the statements of that disconnection statement of the condition, one of the statement of the condition for the condition that makes the subset A and B the disconnection for X is that A intersection B equal to the empty set. Now A and B are both open and closed. Therefore we can write A equal to closure of A and B equal to closure of B. It's because A and B are both open and closed, and since A is closed, then A equal to closure of A, B equal to B is closed, so B equal to closure of B. But we can write B equal to X minus A, since B equal to X minus A, and so by choosing by writing A intersection B equal to empty set, we can replace A and B by closure A and closure B. So closure intersection closure of B equal to empty set. That implies that closure intersection. Now replacing this B by X minus A, since B equal to X minus A, here we can substitute. So closure intersection closure of X minus A is empty. Thus we get the proof in one direction, the completed proof in one direction. Conveys, to prove the conveys, suppose that the statement N is true, then we have that the statement N, that is X has a proper subset A such that closure A intersection closure of X minus A equal to phi. So see here, to get the proof, to get the complete proof, we have to prove we have to use a statement, already proved statement. That statement is that if X is a union of if X is the union of two disjoint non-empty closed sets, then X is disconnected. Since we know that, we have proved that for a topological space X, it is the if X is the union of two disjoint non-empty closed sets, two disjoint non-empty closed sets, then X is disconnected. We can use that result here. Here we know that A is a proper subset of X, and closure of A and closure of X minus A are closed. These are the facts that we know about A. Closure A and closure of X minus A are closed sets, and X minus A is also a proper subset. Since A is a proper subset, then X minus A is also a proper subset. Thus A and X minus A are disjoint closed sets. We have A and closure of A are disjoint closed sets. Okay. So X is disconnected. Using that this statement, using this part of the statement, then we can say that we get a disconnection for X. It's because A and X minus A are not the closed set. Here A closure and closure of X minus A are the closed sets, which satisfy the condition that they are separately, they are non-empty sets, and they are disjoint, and also their union. We can write the union equal to X. Their union, it's because so X has the proper, since X has a proper subset A such that such that closure of A intersection closure of X minus A equal to phi. So it satisfies that that condition. Okay, then see, using this part, so X is the union of since we know that X is the if X is the union of two disjoint non-empty closed sets, then X is disconnected. Okay, here the sets closure of A, closure of X minus A, see, closure of A, closure of X minus A they are closed sets, and we also know that A union closure of and X minus A union X minus A equal to X already it is there. So A union X minus A equal to X, and so if you take the union of their closures, closure of A union closure of X minus A, that will also be equal to X. Thus we get that closure A union closure of X minus A, or the union of these two sets, equal to X, and it is given that closure of A intersection closure of X minus A is empty, and A is a proper subset, so X minus A is also a proper subset. Therefore closure of A and closure of X minus A both are proper subsets. Moreover, we get that their union equal to X. Thus, using this statement, we can say that the set, the space, the space X, the topological space X is now disconnected. Okay. See the theorem 5.11. The theorem 5.11 it states that let X be a connected space, and F which is defined from F is defined from X to Y be a continuous function from X on to the space Y, and then Y is also connected. This theorem its own connectedness and continuous functions. Okay. This theorem says that continuous functions can transfer the property of connectedness to its images. So let's once again read the statement. Let X be a connected space, and F is a function defined from X to Y. It's a continuous function from X on to Y. If it is a continuous function X on to Y, that means there is no point left in Y such that those points do not have any pre-image in the first space. And then Y is connected. Y is now Y is the image space of the space X under the mapping F. To prove this, we use the contrapositive form of the proof. So for that, let's assume that Y is not connected. Actually, we want to show that Y is connected. So if we assume that Y is not connected, to complete the proof, we need to derive a contradiction, or we need to develop a contradiction from the procedure that we follow, that we accept and follow. So then there exists, but since Y is assumed to be disconnected, there exists two non-empty open disjoint open sets A and B such that they make the disconnection. That means A and B there exists such that A equal to Y equal to A union B, A intersection B equal to empty set. A is non-empty, B is non-empty, where A and B are open sets in Y. Next we consider the inverse images of the open sets A and B. So inverse images are F inverse of A and F inverse of B. We consider these inverse images, and these are subsets of the space X. Clear. It's clear that F inverse of A is a subset of X and F inverse of B is also a subset of X. And we are now going to state and establish to 3 or 4 properties of these open sets. And these are pre-images. Okay, and these pre-image sets, the properties of all we shall state and prove the 4 properties of these sets F inverse of A and F inverse of B. First of all, these sets are open, both open in the first space X. We want to show that we argue that both these sets F inverse of A and F inverse B of B are open in X because of the fact that F is a continuous function. Since F is a continuous function from X on X to Y, X on to Y, it is clearly it's very clear that F inverse of A and F inverse of B must be open in X. It's because A and B are open sets in Y. Second property of F inverse of A and F inverse of B are they are disjoint. F inverse of A and F inverse of B are disjoint subsets of X. It's because F is a function. We know that F is a function. So if they are not disjoint, then you can write F inverse of A intersection F inverse of B is non-empty, and you can take an element from that non-empty set. Let X be an element of F inverse of A intersection F inverse of B. Then think about F of X. We can think about F of X. F of X is a member of Y, the second space. F of X is a member of Y. Moreover, it's a subset of F, a subset of A. It's because X is a member of F inverse of A, so F of X is a member of A. Similarly, X is a member of F inverse of B, so F of X must be a member of B, and that means there exists a common point in A and B. For A and B, there exists a common point. That's F of X is a common point for A and B. That is A intersection B is non-empty. A intersection B is non-empty, but this contradicts the fact that A and B make a disconnection for the space Y. Since A and B is assumed to make a disconnection, since A and B are chosen such that they make a disconnection for the space Y, A intersection B must be must be an empty set. Thus we get the contradiction. So here by proceeding using the steps that that F inverse of A and F inverse of B actually is non-empty, we got the fact that F of A, we got the fact that Fx belongs to both A and B, and we get the contradiction, and therefore we have to correct the statement, the assumed statement that F inverse of A intersection F inverse of B is not empty, so it must be empty. The third statement, we want to show that F inverse of the third property is that F inverse of A is non-empty and F inverse of B is non-empty. So for first of all, we can choose we choose to prove that F inverse of A is not empty. Suppose not, F inverse of A is empty. Suppose that F inverse of A is empty, and then we get that A is empty. If F inverse of A is empty, then there is no point in F inverse of A. So if we take the image of that F inverse of A, then you are going to get an empty set as its image set. But you know that A is non-empty. because A and B make a disconnection, so A is non-empty. Since A is non-empty, and getting that f inverse of A, f of f inverse of A, that actually it's equal to and actually it is equal to A. It's empty. In one way we get that A is empty, and the other way we know that A is non-empty. Thus we get the contradiction. Therefore we can correct the statement, the assumption that f inverse of A is empty. So f inverse of A must be non-empty. Similarly, we can show that f inverse of B is also non-empty. Now the fifth property is that their union, f inverse of A union f inverse of B equal to X. It can be established by taking that X is equal to f inverse of Y, because X is mapped to Y onto f is mapped X is mapped onto Y using the function f. So X can be written equal to f inverse of Y, and that is equal to f inverse of A union B, because Y is equal to A union B. That equals f inverse of A union f inverse of B. So this is the splitting of the single expression, and the statements 1, 2, and 1, 2, 3, and 4. So the statements, or the properties 1, 2, 3, and 4 can together imply that X is disconnected. It's because the open sets f inverse of A and f inverse of B are really making a disconnection for the space X, and this fact actually contradicts the accepted nature of X, that is X is connected. So it actually contradicts the accepted fact that what is accepted fact X is connected. It's an accepted fact. So because in the statement it is given that the space X is connected. See, let X be a connected space. So this is a true statement. X is a connected space, or it is accepted as true about the space X. So finally, at the end of the proof, we get that X is disconnected. So and hence we get the contradiction, and therefore we have to correct the assumption that Y is disconnected. So Y must be connected. Therefore every continuous image of a connected space is connected. We have a corollary that can be proved based on the previous result. If f is defined from x to y is a continuous function and x is connected, then f of x is also a connected subset of y. See, f is a function, it's a continuous function defined from x to y. Then we know that f of x is a subset of y. It's also given that x is connected. X is also connected. Since f of x is a subset of y, using the previous result, we can argue that f of x is connected. See, it's because fx is the image of the function f, and also f is defined from x onto f of x. Since f is defined from x onto f of x, we can apply the previous result and get that fx is connected whenever x is connected. So if x is connected, then we get that fx is connected. So that's an application of the previous result. Hence we get the proof of the corollary. Okay, next we have a problem to solve. Problem number 5.13 show that connectedness is preserved by continuous functions. See, it's very easy. It's because in the light of the previously proved results. So in the previously proved results, we have seen that if X is a topological space and it is connected, and if F is continuously mapping X to either Fx or it is continuously mapping to mapping onto Y, another space Y, then its image space is connected. And so what does it mean? It means that the continuous functions can preserve the property of continuity, property of connectedness. See, continuous functions can preserve the property of connectedness. In other words, if a space X is connected, and if F is a function applied continuously or acting continuously on the space X, its image that image is f of X. The image space f of X will also be continuous. Okay, so it's also connected. See, suppose X is connected, and the function is continuous. If the function is continuous, and its image space is f of X, then connectedness, the property of connectedness will be then transferred to the image space. The image space here is f of X. So if X is connected, then f of X is also connected. Okay, and that's all about the results on connected spaces or disconnected spaces. Thank you.